All right, AP Physics C. So here's the question that we have first. We have two masses that are suspended from a rod, and the rod is at equilibrium, so we know it's balanced. We have a larger mass here, and we have another mass here, which we don't know what it is, but we do have two different lengths. And we've got the same setup over here, but you'll notice that this is a different known mass, and then we have unknown mass again. So the two masses here and here are the same mass. We've just replaced the position of that mass, and then we've put some different masses on to kind of figure out what's going on. So the first thing that I think we need to do here is recognize that if it's balanced, the sum of the torques should be equal to 0. So the sum of the torques should be equal to 0. That means that the torque of the one on the left-hand side for each case should be equal to the torque on the right-hand side for both cases. So let's just talk about torque here. It would be mg, which is a force, times L1. And then this one is capital M1G times L2. This one is M2G times L1. And then this one is M times G times L2. So we said that the torques on each side need to be the same. So now we have this really great situation, and then there's a little trick we can use in algebra. If I know that 1 is equal to 1 and 2 is equal to 2, I could put them basically just divide each one. So 1 over 1 is equal to 2 over 2, and that gives me 1/2 is equal to 1/2. We're going to do the same thing with what we have here. So I've got mg L1 is equal to M1 GL2, and I'm going to divide that by this. So this one is M2 G, M2 GL1 is equal to MGL2. At this point, we notice that the G's and the L's cross off everywhere. And so now what we're left with is M over M2 is equal to M1 over M. If I cross multiply, I'm left with M squared is equal to M1 times M2. And if I solve for M, it is just the square root of M1 times M2. So we know that the answer has got to be this one. One of the things you should have caught right at the beginning is if I multiply these two, that gives me a kilogram squared unit. And they want to know the value of M. Well, it can't be kilograms squared, so that can't be right. Same thing for this one. So the only answers could be A, B, or E. So if you weren't sure how to do it, one of the things to do is check units on things. If they don't work out, you can cross those off. Then I had 3 to pick from. But using this algebraic trick makes it a lot easier to do. For number 13, I've got a figure skater who's spinning on frictionless ice. Her arms are fully extended. When she drops her arms to the sides, they want to know which of the following correctly describes her rotational kinetic energy and her angular momentum as her arms fall. Well, we know that angular momentum is always conserved, so it can't be B, C, or D. And we know that the kinetic energy most of the time changes. So just by pure guessing, we can pick letter E. The biggest thing here that happens is when she has her arms out straight like this, and then when she drops her arms, that actually takes work. So when her arms go, and now she's got her arms are really long there, so better make her legs a little bit longer too. When she drops her arms down, that takes work. And that work then will come from the kinetic energy. So her kinetic energy here, when she does work, she's going to increase her kinetic energy. So it cannot stay constant. And that's probably the easiest way to remember that problem. For the next problem, it says you have a bowling ball of mass M, and it has a radius of R. So we'll move back up to this one again here. It says the moment of inertia of the ball about its center is 2/5 mr squared. It rolls without slipping along a surface, speed v. They want to know how high it will roll. So this one's kind of cool because this ball has both translational or linear, and it has angular kinetic energy. Kinetic energy we know is for linear is 1/2 mv squared. And for angular kinetic energy is equal to 1/2 I times omega squared. So same type of thing, just two different ways of looking at it. And as it's rolling, it's got both. So it wants to know what's the vertical height that it can roll to. Well, if the ball is down on the ground and then rolls up, we know that the kinetic energy that it begins with should be equal to the potential energy due to gravity at the top. Potential energy due to gravity we know is mgh, and our original kinetic energy has got to be the sum of these two. So let's figure out what our original kinetic energy is. It would be 1/2 of mv squared plus 1/2 of I omega squared. Now we need to get both of these into the same thing, so we need to convert this into a linear form of kinetic energy so it looks more like this. And we can do that because we know it doesn't slip. So let's go ahead and start doing that. This is 1/2 mv squared plus 1/2. Now we can do our rotational moment of inertia here. So it's 2/5 m times r squared, and then we have omega squared. Now our problem is we need to get to v. So if you remember, v is equal to omega times r, so our linear is always equal to our angular times the radius, and we're going to go ahead and make this a capital R. So now we can rewrite this equation as 1/2 mv squared plus 1/2 of 2/5 times mr squared, and then omega squared. So omega here is equal to v over r, and if I square it, it's going to be v squared all over r squared. The r squareds go away, and our next equation then is 1/2 mv squared plus 1/2 times 2/5 times m times v squared. So at this point, so we can go ahead and leave this in here. We need to do a little bit of our algebra. So I've got 1/2 times 2/5. So I'm going to have 1/2 of mv squared plus, this would be 2 over 10 times mv squared. And I want to make this something over 10, so I'm going to multiply both the top and the bottom by 5. If I do that, I'm going to get 5 over 10 mv squared plus 2 over 10 mv squared, and if I add them, I get 7/10 mv squared. So if this is 7/10, then it's also going to have 7/10 for us to do for the potential energy. So let's think about height. If this is 7 over 10 mu g, and that's equal to mgh, we can ignore the m's since they can cross off, and now we're left with 7 over 10, and the g goes on the bottom, and that would be, times v squared, and that would be equal to h. So we really took this equation and set it equal to this one, the mgh. So this is really 7/10 mv squared. The m's cross off, the g goes down on the bottom, the v squared stays on top, and we've got our h, and so our answer has got to be letter D. And that is number 14. For the next one, which is number 15, this one's really pretty simple, not a lot to it. We'll go ahead and move down to number 15. It says I've got which of the following diagrams here is the torque about point O equal in magnitude to the torque about point X in our diagram. So it says all the forces lie in the plane of the paper, so there's nothing coming out or going in. So we're able to kind of just look at it. We know that torque here is just equal to R cross F, and we know that the size of which is really RF times the sine of the angle. Okay, so if we look at letters C and D, those two here, they've provided us with the wrong angle. So we're really not worried about this angle here, okay? We're really not worried about this angle here. They've done that wrong on purpose. So the appropriate angle for C is not 60, it's really 30, because we're really worried about the angle that's right here. And then for this one, for angle D, it's the complement also. So it's really this angle right here and not the one to the horizontal. It's just crazy. So this one should be 60. This one should be 30. So they were evil when they wrote this question and they did that to us. For this one, we know that it can't be A because if it rotates and this is 2F, you're going to have a lot more torque. So that can't be right. It can't be B because that's half. So that wouldn't make any sense either. So now we've got to look at it where if I double the force, which of these two is going to give us the same answer? And so for letter C, you can take 2R times F times the sine of 30 degrees, and that gives us R times F, which is really L times F, and that's the same as this one. So the only answer you can pick for this one is letter C. That's a really kind of an evil thing to do. And that is number 15, and we will stop on that one.